Welcome back to Physics 30. This is the CO2.4/2.5 section. I have them combined together. So conservation of energy and momentum in collisions and elastic collisions in one dimension. So here we'll look at applying the laws of conservation of momentum and energy to problems involving elastic collisions specifically, and explain what is meant by a perfectly elastic collision. So during most collisions, we usually don't know how the collision forces varies over time, and so analysis using Newton's second law becomes difficult or impossible because of those forces. But by making use of conservation laws for momentum and energy, we can still determine a lot about the motion after the collision, given what's going on before. So again, quite often we don't know the forces involved, so figuring out what's going on after can be a little bit difficult. Earlier, we saw that in a collision of two objects such as billiard balls, the total momentum is conserved if the two objects are very hard, and if we assume there's no heat loss or other energy produced during the collision, then the total kinetic energy of the two objects will be the same after as it was before. So again, we're assuming here that we're not transferring energy into heat, friction, etc. For the brief moment during which the two collisions are in contact, some or all of the energy is stored momentarily in the form of elastic potential energy. But if we compare the total kinetic energy just before the collision with the total kinetic energy just after the collision, they are found, and if they are the same, then we say that total kinetic energy is conserved. Such a collision is referred to as an elastic collision. So again, assuming no energy transferring into heat, etc. If we use subscripts A and B to represent the two objects, we can write the equation for the conservation of kinetic energy very similar to the momentum. So before we looked at total momentum before versus after, we do the same thing with kinetic energy. And if we have two objects, A and B, we have kinetic energy of object 1, or A, kinetic energy of object B, add those up, and I'll get the same sum after. And that is true for elastic collisions. So you'd have to be told that it's an elastic collision, and then you can make the assumption that the kinetic energy is conserved. And again, the primed quantities, so the little raised, almost an apostrophe, means after the collision, and unprimed means what happens before, just like we looked at before. On the next page here, at the atomic level, the collisions of atoms and molecules are often elastic, but in the macroscopic world, where we see things, ordinary objects, an elastic collision is an ideal that is never quite reached because you always have a little bit of thermal energy being produced during a collision. Also perhaps sound and other forms of energy. The collision of two hard elastic balls such as billiard balls, however, are close to being perfectly elastic, and we often treat them that way, even though of course we hear them hit each other, and of course that's going to be an energy transformation. We do not need to remember that when kinetic energy is not conserved, the total energy is always conserved. Collisions in which, so yes, the kinetic energy is being transferred into another form. It's not like we lose kinetic energy, it's just simply being changed into some other form. So the total energy is always conserved, it's just that kinetic energy in our macroscopic world changes into something else. Collisions in which kinetic energy is not conserved, such as everyday life collisions, are inelastic collisions. So you can see most collisions are inelastic. The kinetic energy that is lost is changed to other forms of energy. So ideally, the word lost shouldn't be used there. It should be converted or changed. The total energy is always, so we have the total energy before equals the total energy after. It's just that the total kinetic energy will be less because some of it is transformed into other forms of energy, whether it's thermal or something else. We now apply the conservation laws for momentum and kinetic energy to an elastic collision between two small objects that collide head-on, so all the motion is along a line. To be general, we assume that the two objects are moving and their velocities are VA and VB along the x-axis before the collision, and after the collision, they're primed. For any v greater than 0, the object moving to the right, and v is less than 0, moving to the left. So we kind of assume it's on the x-axis. From conservation momentum, total momentum before equals total momentum after. If it's elastic, then kinetic energy is conserved. Total kinetic energy before kinetic energy after. We have two equations, so you can solve for two unknowns like you've done in an earlier math course. If we know the masses and velocities before the collisions, then we can solve these two equations for the velocities after the collision, VA prime and VB prime. We derive our helpful result by rewriting the momentum equation. So what we did over here is that with that first momentum equation, so this one over here, we bring all the A's to one side and all the B's to the opposite side. And of course we can factor out MA because before and after and before and after. And then take the kinetic energy equation, bring all the A's to one side, the B's to the other side. So take this piece here, move it to here, take this, move it to here. We get that. And then of course we can combine the two equations, and what we end up with are these two scenarios here. So we get either this, or if we factor out a negative here, it can become this. So either way is correct. Now these use when there is an elastic collision, because I use those two equations, the conservation of momentum, which is true all the time, and then I use the conservation of kinetic energy, which of course is only true when it is an elastic collision. Okay, and we'll see how we use this in this next example. And of course, you'll get a reference sheet that has all of these formulas on them. So if we look at this, a 0.45 kg hockey puck moving to the east with a speed of 5.8 meters per second has a head-on collision with a 0.9 kg puck. So it could be a stack of two pucks. Stack of two pucks. Assuming a perfectly elastic collision, so I will use this idea here, what will be the speed and direction after? So this is a case, what we did previously was we would do the similar question with conservation momentum, but I'd know one value after and just solve for the other. But in this case, I don't know both velocities after. So let's look at, so we'll solve by conservation of momentum like before. So momentum of one, or let's see, I'll call it A and B like I did. Momentum of A plus momentum of B equals momentum of A after and momentum of B after. And of course, this breaks down into MAVA plus MBVB equals MAVA prime for velocity after and MBVB prime after. So what I'm told here, I know the mass of both items, so object A versus object B, so I know that and I know that. I know that A is moving 5.8 and this one's at rest. And I don't know either MA prime or V prime. Because when I did this before, a few videos ago, we knew one of these velocities and we could figure for the other. But hey, this is a scenario in which I know the initial parts, and of course due to the difficulty of calculating forces involved, it's difficult to figure out what those are after. But for elastic collision, so for an elastic collision, if I look at this, I know that VA minus VB before is equal to V prime B minus V prime A. So what I could do, I could either solve for either this or this. So I think what I chose to do here is I try to isolate VB prime. So add VA prime, add VA prime, and I get VB prime is equal to VA minus VB plus VA prime. So I have that, and what I can do is I could substitute that into here, and then I'll only have one unknown, as you'll see. So if I rewrite this equation now, I have the first one for A, first stuff for B, oops, MAVA prime. And then here I'm going to have mass of B, instead multiplied by V prime B. V prime B can be represented like this. And in fact, I know what all the VAs are. So I know what all these values are, because I'll be able to figure, I know what VA and VB are, and I can solve for V prime A. But what we'll maybe do is we'll stop the video there because we're over 10 minutes, and we'll come back in the next video and finish this question.